All right, so let's talk about electrical potential. Electrical potential is potential energy. Think, back to gravitational potential energy. It's just there's a bunch of types of potential energy, aka stored energy. So this would be electrical stored energy, right? Electrical potential is the amount of potential energy per unit test charge stored in an electric field. So if I have an electric field like this one from a point charge, a positive point charge, or this one here from two parallel plates, there's an electric field, and thus there is energy stored in it. You can see that. What if we put a positive test charge right here, and then I let it go? Well, there is some energy stored, some potential energy stored, because this thing would accelerate away, gaining kinetic energy. So the potential energy would get converted into kinetic as it flies away. The usefulness of electrical potential is that we divide out the test charge, or in the case of the example over here, the positive charge, right? It's how much is purely stored in the electric field, negating, if you will, the thing that's put into the electric field. So V, or your electrical potential, units of volts, is the potential energy. U, if it makes you more comfortable, you can write in PE there. U, PE, same thing, divided by Q, or the test charge that you put into the electric field. Now, just knowing one voltage, like knowing just knowing one electrical potential, like the electrical potential there or here, isn't overly useful. On the other hand, having a electrical potential difference, we sometimes use the term voltage for that. The electrical potential difference between here and here, an object moves between those two, that's more useful. So delta V, or the change in electrical potential, aka the voltage, is equal to the change in potential energy, how much potential energy is lost or gained, divided by the charge that moves between those 2 points. So this equation is much more useful. It is a scalar quantity, and it is a conservative quantity, electrical potential, that is. It's all dependent upon how far away you are from a charge and what the charge is. If we're dealing with point charges, this would be the equation for a point charge there. So, for example, these are equal potential lines here. It doesn't matter where you are along these lines, you're going to have the exact same electrical potential, because the radius r is still the same and the charge is still the same. It's a conservative quantity, meaning it's path independent. It doesn't matter if, let's say we were looking at a change in electrical potential of voltage going from here to here. It doesn't matter if I go from here to here, or if I come and I loop all the way around and I end up there. It doesn't matter if I loop all the way around and I end up over there, because the voltage difference is still the same. It's path independent. Now, if we're looking for just the electrical potential of an object, using this equation for potential energy that is stored between two charges, Q1, a large charge producing an electric field, let's say, Q2, a charge getting pushed around, or a test charge, inside, divided by the distance between them, substituting that into this equation over here, I get this one. The electrical potential equals K, Q, that is producing the electric field, right? That's producing the electric field, divided by R, the distance to the spot that I care about the electrical potential.
Now this equation becomes very useful whenever you take this equation and you solve for the electrical potential at two different spots, let's say here and here on those two lines, and then now you take those two electrical potentials and you substitute them in for electrical potential difference, or voltage, which then lets you calculate change in potential energy. If you know the charge that's moving, this change in potential energy can be converted, depending on what the energy is being converted into work. It can be converted into kinetic energy, and it can be used to solve whatever problem you might encounter. Over here we have two parallel plates. I have a positive plate and a negative plate. Now, in between two parallel plates, the electric field is constant. It does not decrease with distance, and so the equation for electrical potential is V equals the electric field, so electrical potential equals the electric field times the distance between the two plates, or another way to put this is the electrical potential of a particle, or if we want to put a delta in front of this, delta V could equal E delta D, where E is the electric field and delta D would be the change in distance of, let's say, a particle between two plates. All right, so in this problem, I have two charges, or I have a charge, excuse me, Q, of 3.2 microcoulombs. And then I want to know the electrical potential difference between point A and B. The entire idea behind this problem is I'm going to let some positive charge, aka a proton, I'm going to let that move from B to A. And remember, it's equal potential, so it doesn't matter how it gets there, right? It can go all the way around like that. It can zigzag like this, or it could just go straight from B to A. Doesn't matter. First thing though, what is the electrical potential difference, aka the voltage between the two? Now I give the distances to B and A and the charge for Q. And so what we're going to do is we're going to calculate the voltage at B, and then we're going to calculate the voltage at A and subtract. All right, so we're going to use these two equations right here, or it's the same equation, excuse me, V equals KQ over R, electrical potential equals K times the charge producing the electric field. That's what we know about. We know about the charge producing the electric field divided by the distance to the spot that we care about. The equation of V, or delta V for potential difference, equals delta U over little q. That's all about if we know a charge that is moving inside of an electric field. And I know nothing about some small charge moving inside of it yet. I know about a large charge producing a potential difference, producing an electric field, so producing a potential difference A and B here, right? So after I plug in all my numbers here, distance out to B, right, I said was 0.500 meters, and the charge producing at Q is 3.2 microcoulombs. That's why times 10 to the negative 6 there, right? Coulombs, base unit for charge. Micro means I need to put on it times 10 to the negative 6. I come out with these two voltages. Now, change in voltage is final minus initial, and I'm letting, I said, the charge move from B to A, meaning that the final position is A, which is further out, so it's going to have a lower electrical potential than further in, B, the start, which, closer in, has a higher electrical potential, giving me a potential difference, or a voltage, of a negative 28,800 800 volts unit for electrical potential, or electrical potential difference, volts. I'm not rounding for sig figs here. I'm going to round for sig figs at the very bottom. All right, so the next question, what will be the change in the potential energy if we let a proton move from B to A? So now that I know what the potential difference is between B and A, I know the electrical potential at B, I know it at A, subtract, and I get the potential difference. I can calculate what's the change of potential energy of a specific small particle, a proton. So now I'm putting in some small particle at B, and I'm going to allow it to move to A. So since we're dealing with a small particle moving inside and its electrical potential difference, or voltage, I'm using the equation delta V equals delta U, right, a change in potential energy, delta U, divided by Q. And I know delta V now, it's negative 28,800. Delta U, the change in potential energy, is what I want. What will be the change in potential energy? And we're doing it of a proton, and we know the charge of a proton. It's 1.6 times 10 to the negative 19th coulombs. And whenever I substitute this into my calculator, I come out with negative 4.608 times 10 to the negative 15th joules. Once again, not rounding for sig figs to the very bottom. Unit for energy. This is just traditional potential energy, change in potential energy unit, joules there. Also, this would be a good time to mention, whenever you're plugging into voltage equations, right, or electrical potential equations, please actually use the charge, right, whether it's positive or negative. In all the previous ones with electric fields and with Coulomb's law, I said always use the absolute value of charges. You're going to assign direction manually yourself on your free body diagram. So the positive and negative of the charge, because positive and negative only means direction, is going to end up messing you up. But here it actually helps you because there's no free body diagram. Voltage is really the same thing as conservation of energy. This is a conservation of energy problem whenever it comes to static electricity. So we need to use the positives and negatives of our charges. That way we know if the thing is gaining energy or losing energy. So like here, a negative potential energy, meaning we are losing electrical potential, we are losing potential energy. All that potential energy, though, is getting converted to something. All the potential energy is getting converted to kinetic. So down here, how much kinetic energy will a proton gain? Well, it's going to gain Ke. It's going to gain 4.608 times 10 to the negative 15th joules of energy. That's how much it gains. It loses that much kinetic, and so it gains delta Ke that much. So now lastly, what will be the final velocity of the proton as it moves from A to B? Well, I know an equation for kinetic energy. Kinetic energy is going to be Ke, and this is technically delta Ke, 1/2 mv final, if I'm using delta Ke, 1/2 mv final squared minus 1/2 mv initial squared. And if I assume in my problem that the initial velocity is 0, I release a proton at B, that means this all goes away over here, right? That part completely goes away, just leaving me with kinetic energy equals 1/2 mv final squared, where I'm looking for the final velocity. Once I substitute everything in, right, kinetic energy, mass of a proton, you know it's a constant, it's given to you in your packet, so don't ever worry about that. If you ever see the word proton or electron in there, or this many protons or this many electrons, you automatically know mass and charge. So the word proton tells you mass and charge because the mass and charge of a proton are given to you in your packet. So whenever I go through the simple algebra, plugging all this through, so divide over by half, divide over by mass of protons, square root, then in the end, I come out with a velocity of about 2,300,000 with sig figs meters, 2,300,000 meters per second is my velocity, and here it is in scientific notation. Now, with that in mind, this proton really ends up moving quite quickly at the very end. In fact, we could talk about in terms of percentage of speed of light, but I'll save that for class there. Another thought for you about this. You might want to try to solve this using Coulomb's law, but that's not actually possible because you see the force on this proton is changing. Because if you say, okay, I know this Q and I know the Q on the proton, and so what I'll do is I'll set up something where I solve using Coulomb's law, right? F equals K Q1 Q2 over R squared. I solve for my F and then I substitute that F into F equals MA, and I solve for A, and then I take that A and I substitute in some kinematic equation like Vf squared equals Vi squared plus 2A delta X. I know the distance between them, and I can solve for my Vf. The reason this doesn't work is because our F is actually constantly changing according to R squared. So the F here is not the same as the F here, is not the same as the F there. It's decreasing over time according to R squared. So if you don't have the same number F, you can't substitute anything in there, and you can't substitute any A in here because it's constantly changing too, and without calculus-based physics that's no good. The beauty of conservation of energy is it can handle a changing F because direction doesn't matter with it, and that's what electrical potential difference problems really are. It's conservation of energy.